Here we go, 5 degrees. There are 4 parts to the answer. Smaller. The first part is you have to mention something about the rays of the angle. That's the first point. Second point is that those rays cut off. Or it's not showing up. Yep, I got it. How about now? Can you read it yet? Cool. All right, an angle of 5 degrees. The rays of the angle, that's first point. Cut off, sub 10, that's the second point. 5 360ths, that's the third point of the circumference. For 4 points. 1 point for each one of those things that you mentioned. Did you mention the rays? Did you mention cutting off or subtending? That's 2. Did you mention 5 360ths? That's 3. Of the circumference, that's 4. So out of 4. So 5 radians, everything will be the same except what? So the rays still cut off, but now they cut off what? 5 radius lengths of arc length along the circumference. The rays of the angle cut off 5 radius lengths of arc on the circumference. So 1 point for rays, 2 points for cut off. 1 point for 5 radius lengths, and then 1 point for circumference. And then how is 5% different? So we still got the rays cutting off. Now what do they cut off? 5% of? 5% of what? The circumference. Or you could say 5/100ths, or you could say 5%. If you said 5%, that's fine. So now 5% would be the rays cut off, so 10, 5/100ths of the circumference. So is that 12 points? Okay, take your total out of 12 and add 8. Nice adjustment. Yes? I'm suspecting that this didn't go so well, but it's more about the learning experience. Like, so we got to take the deficient understanding or minimal understanding, and we got to make it full understanding. So that this is more about the learning experience. So take your square out of 12, add 8, and then write that total out of 20 on the top. So whatever you got out of 12, add 8, and the quiz is out of 20 now. So if you got 5 points in the first 3, you're going to add 8, 13, you have 13 out of 20. Just use your best judgments. I'll trust you. Because I can't do that with everyone. We got to move on. So just use your best judgment. Okay, and then make sure your name's on it. You got a score out of 20. And turn it over and pass it in toward the middle. This is one side of these. Okay. Okay. So we're talking about radians. It all began with this. Can you see the circle? As long as you can barely see it, that's fine. That's all we need. But there's a circle there, okay? And we began with this, which represented what? The radius of the circle, okay? And we looked at different circles. So this could be any circle, okay? This could be radius of 2, or 0.2, or 200. And what did we do? We took that radius off from its normal spot, and we didn't use that slider to do it. Okay? So we took that radius from its normal spot, and we wrapped it on the circle, maintaining that radius length. And we said that so if we looked at the terminal side at the 3 o'clock position, remember, so this is the 3 o'clock position, and we swept an angle counterclockwise from the 3 o'clock position, that one radius length would define an angle, right? Maybe. There we go. So that radius length, one radius length, defines some angle swept counterclockwise from the 3 o'clock position. And since it's cutting off one radius length, we called that angle what? The openness was 1 radian. The openness in radians comes from the number of radius lengths cut off by the rays of the angle. It's the same as the number of radius lengths cut off by the rays of the angle. Has it sunk in yet? There's a question on the test, and it tells you how many radius lengths this thing has gone around a circle. And then it says, how many radians did the thing rotate? It's on the test. Get it right. Because it gets like 50%, it gets like 50% success. Okay? It tells you how many radius lengths something went around a circle. And then it says, how many radians did this thing rotate? What's the answer? The same as the number of radius lengths that this thing went around the circle. That's what radians are. It's the number of radius lengths cut off by the rays of the angle. That's where radians comes from. Okay, so that's 1 radian. And then we said, so here is 2 radius lengths. Two radius lengths. What's the openness of that angle? 2 radians. I'm going to beg the... Okay, this is 3 radius lengths of arc length. What's the openness of the angle? 3. Okay, so we can keep going. That tick mark is 4. That's 4 radius lengths, therefore 4 radians of openness. That's 5 right there. That's 5 radius lengths around the circle. So it's 5 radians of openness, the angle. 6. There's 6. So all the way around is some amount, somewhat, maybe a quarter more. You need about a quarter more of a radius length to get all the way around. Lots of people in the last class were in several different contexts. They were always concluding that it was 6 radius lengths all the way around. Is it 6 radius lengths all the way around? No, that's 6 radius lengths. It doesn't make it. You need about another quarter of a radius length to get all the way around. So, what about these positions on the circle for whole numbers of radius lengths or whole numbers of radians? Do they coincide with kind of nice symmetric places? You should clearly see that they're not. They don't really align themselves with the axes or cutting things in half, or just kind of in abnormal, asymmetric places on the circle. So that's why at the end of class we talked about it'd be really nice to know exactly how many radius lengths to get exactly halfway around. And we said, oh, there's 3.1. That's not quite far enough. And then we said 3.2 was too far. And so how many radius lengths to get exactly halfway around? Yeah, that's one definition of pi. This is one possible definition of pi, that if this is 3 radius lengths right here, then we need a little bit more, like 0.15, or more exactly 0.14159. And so halfway around the circle is exactly this irrational number pi. Pi radius lengths to get halfway around. Therefore, all the way around, is it 6? No, this is 6 radius lengths. Doesn't make it. So exactly all the way around is how many radius lengths? 2 pi. Is it 6.28 all the way around? Is it 6.28 radius lengths all the way around? John says no. Is that too short or too long? That's a common approximation that people use. But it's not exact. If you want it exact, you've got to say 2 pi. 6.28 is just really close. It's almost there. It's almost enough. It's still not quite enough. So when you use 6.28, just keep in mind that that's an approximate number of radius lengths to get around, not exact. 2 pi would be if you need it to be exact. Okay, so the nice thing about having pi is now we can identify and put a number on these nice places. For instance, the very top of the circle. How many radius lengths to the top? Pi over 2, half of pi. Okay, how about 1/4 of the top half? So we're halfway through. Yeah. So if we're going from if we want to go half the distance along the arc, here to the top would be pi over 4. And then half the distance from the top down back to the middle would be? Okay, we can keep going. This is pretty close to 1 1/4 pi, or 5 pi over 4. Okay, bottom of the circle. So if this is 1 pi and this is 2 pi, then how many pi is at the bottom? So halfway from 1 to 2 is 1.5. 1.5 pi. Okay, and then this would be 1 3/4 pi, or 7/4 pi. 1 3/4 pi. Okay, so in my experience, what I've seen is that students tend to think that when you start working in all these pi values, these kind of become like labels for places. Like, oh, the name of that place is 3 pi over 4. Okay? So I want you to, let's first estimate how many radius lengths it is there to 3/4 of going around the top half. So estimate how many radius lengths to get there. What would you estimate that to be? How many radius lengths to get right there? What do you think? 2.5. So let's do a little better than that. Less or more than 2.5? A little bit less than 2.5. It's a little bit closer to 2 than it is 3. How can we find that exactly? How can we find that number exactly? Yeah, put it in your calculator. Go. 3 pi over 4. Put it in your calculator. Is it what we predicted? We said a little bit less than 5. You should have gotten 2.356. And if we wanted to, ... So what's the moral of the story? 3 pi over 4 is not a name or a label for that point on the circle. It's still a number. And what does that, a number of what? Or an amount of openness, right? 3 pi over 4 radians, or 3 pi over 4 radius lengths, is a number, 2.5, 2.3562, yada, 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 radius lengths along the circumference to get there, or 2.3562 radians of openness, that angle is. Okay, so don't when everything becomes about pi, don't lose sight of the fact that you're still, come on, close enough. You're still talking about a number of radius lengths or an amount of openness in radians. As a number, it's a number. 3 pi over 4 is a number. 2.3562, blah, blah, blah. Okay? So real quick, just some practice. So I'm going to leave the whole number of radians up there. That's the whole numbers. So let's just I want you to estimate these. Okay? So estimate the position of the terminal side of the angle here. So 1.8 radians. Janessa, which quadrant? 1.8 radians. Is it going to be closer here to the y-axis or the x-axis? Terminal side, like closer up here or more down here?
The second one is the one
Near the top. 1.8. That's 1.8. Okay. 0.3. Kate. First quadrant. Closer to here or closer to here? Okay. About 1/3 of 1. That may just a little too big, but that's the right idea. Okay. Maybe a little lower than that. A little bit less open than that. It's 0.3. Okay. 4.25. Fahia. Quadrant 3.
a little bit
Off of, right, so it would be 1/4 more further than, this is 4 right here. So 1/4 further like this. Something like that. That's 4.25. Okay, 6.1. Becca, can you do 6.1? Fourth quadrant.
Like halfway between the x-axis and the fifth.
Halfway here?
And 6. No, up higher. Yeah.
Like there. Oh, halfway between 6 and the x-axis.
Sorry.
That's good. 6.1 right there. Okay, what about -1? What would a negative then represent? Okay, backwards. Clockwise. Okay, so how do I know how far to go clockwise if I want -1? Yeah? Nice. So we're still gonna go 1 radius length, but now clockwise. So he's saying we can use this right here as a reference. It's kind of a symmetric point. So that's -1 radian. -5 radians. First, second, third, or fourth quadrant? First, right? It's going to be here's +5. So you imagine going -5 would put you straight up from there, right? -5 would be right here. Would it be around like this, right? All the way, that much openness right there. -5. Questions on radian angle measure, the basics. Okay, let's go back to 1 radian. And remember this angle measure all began with, what was our strategy at the very beginning for measuring angles? Remember what it was from the very start? What was our strategy for putting a number on an angle? So the very first thing we did. Well, openness is what it's measuring, but then we started putting numbers on it. It was the first way that we put numbers on it. Here's the circumference. What about the circumference? Fraction of the circumference, or percent of rotation. So my question to you is, what fraction of the circumference or what percent of rotation is 1 radian? Everyone figure it out. 1 radian is what in terms of this way of measuring angles as percent of the rotation, or fraction of the radius? Okay? Is that what everyone else was thinking? Carla wants 1/2 pi. Does that give a fraction of a full rotation that is 1 radian? Okay, find that number. Go. Find it. What is it? .159? As percent? 15.9%. So I want to show you something. Having that, if I said how many degrees is 1 radian, then you thought to yourself, what's the formula? But now I just told you that 1 radian was 15.9% of a full rotation. And if I ask you now how many degrees it is, it should seem very simple. Find out how many degrees is 1 radian. If 1 radian is 0.159 of a full rotation, how many degrees is that? What would you do? Zach?
So you take your decimal number,
Yeah.
percent, multiply it with 360.
Yeah, we want that fraction of 360. It's so easy. Do you see? No formula to memorize. We're just going to take that fraction of the circle, and now we want the fraction that is a full degree, a full rotation in degrees. 57 or something? Is it? No formulas to memorize. If you work with percent of the circle, all you need to know is what a full rotation is in radians, which is 2 pi, and what a full rotation is in degrees, which is 360. And if you know those two things, and you just know very basically how to find a percent and how to use percent, then there's nothing to memorize, okay? So let's practice that. Beautiful. Is that, oh good, okay, cool. So what did we say? We looked at 1 radian, first of all, something like that. And we said we started with radians, and where do we go next? Go to home base. What's home base? Percent of the circle. So to get the percent of the circle, we took 1 divided by 2 pi, and we got 0.159 of the circumference, or of a rotation, or 15.9%, 59.9%. And then we took that percent of 360, and we got the number of degrees. Maybe that. This one. Let's draw it. So we had one radian. Take 1 over 2 pi. That gives us 0.159. And then what do we do? Times 360 gave us 57.3 degrees. Is that right? Nothing to memorize. If you always do your first step, find the percent of the circle that you're dealing with. Then you can get anything else really easily. Okay, so I want you to find how many radians is 208 degrees. 208 degrees. How many radians is 208 degrees? First of all, what quadrant are we in? Think about that. And where in that quadrant? Everyone think about that. Which quadrant and where in that quadrant? (208 degrees). Which quadrant and where in that quadrant? How about Cameron? Which quadrant and where in that quadrant? 208 degrees. Third? Okay. Tell me where. Closer to this side or closer down here?
Closer to the
Up here. Yeah, it's just a little further than halfway, right? Because halfway is 180 degrees. So 208 is like another, 28 degrees. Okay? So John, what are we going to do first? Divide by 360, what does that give us? Percent of the circle, right? We're going to take 208 over 360. Here's the thing. You can get a decimal version of that or not. You can get a decimal version, or you can just keep it as it is. But if you want it, what is the decimal version of that? 0.57? One more decimal place. 578? That's what I heard. Is that right? Okay. And how much openness will that be? 0.578 for circumference. How much openness? Where should I stop? Andrew says, thinks I passed it. So where should I stop? Are we changing the amount of openness? No, it's the same. You just say it's the same as the degrees. Same as the degree openness. So now as percent of a circle, it's 0.578 of a circle. How do we get radians from that? Yeah, we want that fraction of a full circle in radians, which is? What's a full circle in radians? 2 pi. So we want 0.578 of 2 pi, which is calculated by? So we're going to take that. We're going to take 0. So you could write 0.578, or you could just leave it as this fraction. Take 208 over 360. So that's the fraction of a full rotation times 2 pi. Or use the decimal in your calculator, whatever. How many radians is it approximately?
3.63.
Don't memorize the formula. This is much better because if you have a lot more flexibility to do anything with this. Always find percent of the circle first, and then take that percent of whatever a full rotation of the unit you want is. Take that fraction of that. Okay, so gradients. Anyone know how many gradients there are in a full rotation? $400 gradients is one full rotation. Or grads. Right, so each quadrant you sweep 100 per quadrant, right? 100, that was why 400 was chosen, right? So because then each quarter is a nice round 100, which is nice in our 10 system. Okay, so I want you to find how many degrees and radians is 79 gradients, 79 grads. How many degrees, how many radians? First of all, what quadrant?
First.
They want first, agree? Closer to the x-axis or closer to the y-axis? Oh, I heard x, y. Right, it's going to be further. It's halfway up in that first quadrant would be 50, or halfway around. 79 is going to be something like this. Find out how many degrees, how many radians. Do it my way. Learn something new. Learn something new. How do we start? Allah.
So I think we are dividing 79 by 400.
I said 79, right? 79 by what?
400.
And what would that number represent? 79 divided by 400.
The fraction of one fraction is 79 of 400.
Okay.
I think this is how I should say.
And that's the fraction that 79 is of 400. And how are you going to use that? So if I say find degrees and radians. What about, let's do degrees first. So how would you get the number of degrees, Allah?
The number is, well, I'm not sure. I didn't move that far.
Okay, so let's go back to this. What is that number? That's 79 over 400. Yes, that is the fraction that 79 is of 400. But more generally, why did you find it? What does that number mean? 79 over 400.
I'm not sure.
Not sure. Someone have their hand up over here? Yeah, Jay. Or sorry. Sean, sorry.
It's percentage of the circle that the angle has.
Yeah, so this is a percent or fraction of a full rotation. Let's get a decimal approximation for that. Sometimes that's easier to see. So what's the decimal approximation for that? 0. So that amount of openness is 0.1975 of a full rotation. So then how would we find out how many degrees that is? Allah. So if we're going 0.1975 of a full rotation, then how would we get degrees?
We will divide it by 360.
How do you get this fraction of 360? We want this portion of 360. We're not multiply, right? Multiply. So it's going to be, then we're going to take that and we're going to say times 360.
Which will give us
71.1.
71.1.
All right. Are we good? 71 degrees? All right, now I'm gonna go, so now I need to figure out radians, so I need to go back here to the 79 to figure out radians, right? Oh, Jake, tell me.
Because the percent of the circle.
Yeah.
Like 79 and 400 are 11.1975.
Right. That's it. So now we want that same fraction of a full rotation of radians times 2 pi. How many radians? 1.24. Does it make sense? Okay, this is the best way to do it. It shows that you're smart. Okay? It shows that you get angles. This, knowing how to do this means you understand angle measure. Okay? So do this. And it's also easiest. There's nothing to memorize. Okay, except 360 and 2 pi, and then maybe 400 for gradients. Okay, so I want to... Are we good? Anybody have a question? So, always first move. If you're given an angle measure, first move, you want it in a different unit, your first move is always what? Get the fraction of a circumference, or the percent of the circle. From that, you can do anything, right? Okay. Okay, I'm going to go back to this. Those are on. Okay, so I want to talk about something you may have heard of before called the unit circle. Is it off? I'm sorry. Thank you. that on? Unit circle has, the center is 0, 0. So we put the circle at the center of our coordinate plane, and we give it a radius of 1. How many circles have those characteristics? How many circles have those characteristics?
All.
What do you mean all circles? All circles have a radius of 1? All circles have center 0, 0? Okay. Well, funny you should say all, because it would appear that this is just one circle. But my point to you was going to be, some of you got it, that this is all circles. This is all circles. So consider an ant walking a circle of radius 14 millimeters. And consider a moon around some planet with a radius of 8.8 billion miles. So on the unit circle, what are the coordinates of that point right there? The unit circle. 0, 1 or 1, 0? We better all know that. 1, 0. If I want that circle to mean an ant walking around with a radius of 14 millimeters, then what does the 1 mean? So I want this to be the ant walking around in a circle, and that radius is 14 millimeters. Then what in the heck would the 1 mean? What is it? She said 1 radius. Does it work? If that's 1 radius, and then for the ant, what's the length of 1 radius? 14 millimeters. So we can measure that as in millimeters, but we could also measure it in radius lengths. So as the ant's walking around, 14 millimeters, how far to the right is the ant right now in radius lengths? How far to the right is the ant in radius lengths when it first starts walking? 1. Number of radius lengths. If 1 means the number of radius lengths and not necessarily axis units, suddenly the unit circle became every circle in the universe, from the tiniest circle, an ant walking in a circle, to a moon revolving around the planet. So, here's our planet now. It's revolving around. What does the 1, so this radius is 8.8 billion miles. What does the 1 mean for the planet? It's still 1 radius length in this view to the right of its planet, the moon. So I should be talking about the moon. Okay. So the moon is still 1 radius length to the right of where its planet is in the middle. Okay, circular orbit. Some moons do have circular orbits. Okay, so then suppose our moon is traveling, or the ant is traveling around and ends up right here. And I come and I look and I say, oh, on the unit circle, that's 0.5. 0.5 what? 0.5 radius lengths up, right? So now, whether it's the ant or the moon, if it's in this spot on its circle, it's 0.5 radius lengths up from the x-axis. So how many millimeters is the ant above its horizontal axis? How many millimeters? 45? How many millimeters is the ant up? 7. It's up 7 millimeters. How many miles is the planet above the horizontal axis? Moon. The moon. How many miles is the moon above the horizontal axis? 4.4 billion miles. Both of them are 1/2 radius length above the horizontal axis. Okay, so this is the idea that the unit circle, this radius 1, if we think of 1 as 1 radius length, then the unit circle is any and every circle that we can model in the universe. Okay? Cool. So now I want you to go to page 265 in your book. Page 265. Okay, so 5.2 feet. So the radius is 2.6 feet. The bug sweeps an arc of 5.2. Something like that. So I think that asks how many radians does the fan rotate? Is that what it asks? So, Zach, right here. How many radians did the fan rotate as the bug traveled 5.2 feet along the arc? Okay, well, where does radians come from? The number of radians is what? The number of radians of rotation is the same as? Where does it come from? What about the radius? Number of radians of openness is an angle whose rays do what? Put off a certain number of radius lengths, right? So how many radius lengths did the bug travel, Zach? How many, if it's 2.6 is each radius length and went 5.2, how many radius lengths did the bug travel? 2. So therefore, what's the angle of openness in radians? 2. So to get radians, you find number of radius lengths. So you're going to take the total arc length, divide it by 2.6. It tells you how many of those 2.6s the bug went, right? You're taking that 5.2 and breaking, you're saying how many lengths of 2.6 did the bug go? And it was 2 radians because it traveled 2 radius lengths. Okay, Maddie, what about, was the next one 11.4? 11.7, something like that, maybe down there? Actually, I think it's in the third quadrant, somewhere more like around here. All right, sorry, tell me, what is it?
11.7
And why do you want to divide 11.7 by 2.6? Okay. Okay. Right. Right. So we went. No, how many 2.6s fit in 11.7? How many 2.6s fit into 11.7 feet? That'll tell us how many radius lengths. And the number of radius lengths is the same as the number of radians. So if we just had any arc length, how could we get the corresponding angle in radians? multiply by the radius length. Or divide. Just do either one you want. Multiply or divide. It works both ways. Divide. Yeah, you're taking the full arc length and you're asking how many of these R's, how many radius lengths fit into S? That's the number of radius lengths, so that's the openness in radians, right? It's the same. Okay? All right, so we're gonna start working on tracking the location of the bug. Tracking the location of the bug as it starts moving from the 3 o'clock position. So this is going to be, we're going to build some functions. So the input quantity of our function is going to be all right, so write this down, memorize it now. You're going to have to write it on at least 2 quizzes. And just learn it now, and then you won't have to keep learning it over and over again. We're going to live in the land of the measure of the angle swept counterclockwise from the 3 o'clock position. And that's the same angles we've been looking at, right? This is just the formal definition for the same angles. Starting at the 3 o'clock position, sweep counterclockwise, and we can use any angle measure unit we want. Radians, degrees, doesn't matter. That's going to be the inputs. Because that's kind of what happens first. So we take some angle measure, and based on angle measure, now we want to get the location of the bug. The location of the bug is going to take 2 quantities. It's going to take not just 1 quantity, but 2 quantities. Okay? The first quantity is related to what we call the horizontal diameter. So what aspect of the position of the bug relates to the horizontal diameter? What aspect of the bug's position relates to the horizontal diameter? Any ideas? Let me give you more to look at. What aspect of the bug's position relates to the horizontal diameter? See what I added to the picture? Okay, it's a distance. What distance? What distance? Distance around the circle? What is it? Vertical distance. So if the horizontal diameter is a baseline, the first aspect of the bug's position we can talk about is the vertical distance above the horizontal diameter. And so that will create one function. If the input is the angle swept counterclockwise, the measure of the angle swept counterclockwise from 3 o'clock, and the output is the vertical distance above the horizontal diameter, we have a function that starts helping us determine the position of the bug. Now, what are we going to measure? That vertical distance above horizontal diameter in. Well, we want it to be universal for any circle. If we say feet, that might not be good for our circle of the moon around the planet, and it might not be good for the ants. So what universal unit can we use for this vertical distance? We talked about it. Radians is openness, so radius lengths. Okay, but what's the most number of radius lengths that quantity will have? Yeah. Where is that?
At the furthest point away from the center circle.
Which is where on the circle?
The 3 o'clock position or the 12 o'clock position.
The 3 or the 12 gives you a vertical distance of 1?
Oh, vertical distance of 1 now. Sorry, the 12 distance.
Right, 12 o'clock position. Yeah. So this is the greatest that vertical distance can be. And in radius lengths, how far is it? 1, right? It's 1. So every other position on the circle is what related to 1? Less than 1. So rather than say radius lengths, we'll say, to be real clear, we're going to say that we're going to measure the vertical distance above the horizontal diameter in fraction of a radius length. We could say radius lengths, that would be fine, but I think this underscores the point that most of the time, we're going to get a fraction of a radius length. Okay? We're not going to ever get 2 radius lengths, right? The most we can get is 1 radius length above at the top of the circle. So it's never going to be lengths, right? It's going to always be a fraction of a radius length. Okay? So what's the other function that we're going to do? The other function will also, the input will also be to measure the angle, so counterclockwise from 3 o'clock. And the other output, if we want to pinpoint the location, what reference will we use now? What else do we need? We're going to need the vertical diameter, and we're going to be measuring what? The horizontal distance to the right of the vertical diameter. Measured in what? What's the most that could, so measured in what unit? Fraction of a radius. The most it can be is 1. Where on the circle is the distance to the right of the vertical diameter equal to 1? 3 and... Okay. What about at 9? So let's talk about 9 o'clock. What is the horizontal distance to the right? That's the best I can do. What's the horizontal distance to the right of the vertical diameter? If we're defining to the right, then we're saying that's positive. So then everything on the left side of the circle will be a negative value from 0 to -1. So that's really helpful because now we know if we got a negative fraction, we know we're to the left of the vertical diameter. If we get positive, we know we're to the right. So there's the first function, and then let's just copy and paste. So say output of function number 1 and then output of function number 2 is going to be, how do we change it? Horizontal distance right of vertical diameter in fraction of a radius length. 2 functions, they both have the same input, but their output is going to be either a vertical distance above the horizontal diameter in fraction of a radius length, or horizontal distance to the right of the vertical diameter in fraction of a radius length. So looking at them both together, oh no. Given an angle, do those 2 output quantities pinpoint the location of the bug? Given an angle. Backwards, sorry. Forwards only. Okay? So, given any angle swept counterclockwise, if we knew that those 2 output quantities, would we know exactly where the bug was? Would that pinpoint the location? That's the point, okay? So we need both of those output quantities to say, this is exactly where the bug is. It is 3/4 of a radius length to the left of vertical diameter, and 1/5 of a radius length above the horizontal diameter. So what I just said was maybe something like this. Unfortunately, those two numbers don't work together, but something like this. Yeah. So how many radius lengths are we above the horizontal diameter? What would you guess here? How many radius lengths right now is the bug, or what fraction of a radius is the horizontal? What fraction of the radius is the bug above the horizontal diameter? What would you say? 3.3. Agree with that? What do you think of it as estimate? 0.3. What fraction of the radius length is the bug to the right of the vertical diameter? Negative 0.8. What do you think? Is this 1/5? Is this 4/5 and that 1/5? That would be 0.8. More or less than negative 0.8, or more or less negative than 0.8. No, this is way more than 4/5, right? Do you see that this is the full radius and we are here? So let's try again. What fraction of a radius are we to the right of the vertical diameter? Negative or positive? Negative 0.9, or maybe even more than that, but we'll just go with 9 for estimate. Okay? Maybe you could even say 0.95, negative 0.95. Okay, cool. So let's use our covariational reasoning to look at that first function. So I've written it again up there. Is it in the screen? How about now? Input, measure the angle. So what, counterclockwise from 3 o'clock. Output. No, I want the other one. Vertical distance above horizontal diameter as fraction of the radius length. Remember our covariational reasoning? So we want to kind of flush out this relationship, or maybe get a graph of it. Okay? How did we do that? Remember covariational reasoning? What was the approach? Look at what? Does anybody remember? Was it? In which one? Input or output? Look at consistent changes of the input, small equal changes of the input, and then do what?
See how the output changes.
Right. So we're going to ask some questions to analyze the output. The first question we were going to ask was the easy question, right? And when we look at equal changes of the input, what does the output do? We said, just does it increase? Does it decrease? Does it stay the same? Easy question, right? For equal increases in input, does the output increase, decrease, stay the same? Then what was the second question? We looked at what? Okay, that's what we're talking about. Y is the output. So we looked at how the output changes. Does it increase, decrease, or stay the same? And then what was the second question we were going to ask? Nathan, do you remember?
How does changes in Y? How do the changes in Y?
Yeah, well said. He said, how do the changes in Y set? So how does each change in Y compare to the previous change in Y? So how are the changes changing? Okay, so here's that. Can you read that? So for equal increases of the input, does the output increase or decrease? Do changes in the output increase or decrease? And then does the rate of change increase? And then to help us with number 2, we ask the question, do the changes become more positive, less positive, more negative, or less negative? And that was to help us look at how the changes were changing. So what I've got here is equal increments of pi over 8. Okay, so equal increments of pi over 8 so that it takes 8 chunks to get halfway around, and then 8 more chunks to get all the way around. That's equal increments of pi over 8. Okay, so here we go. Let's do it fast. First change in x. First pi over 8, or first change in input. Pi over 8. What happened to the vertical distance above the horizontal diameter? Increase or decrease? Increases, and I'm showing you the amount of increase right here. Okay? Next, equal increment of input. What happened to the vertical distance? Did it increase or decrease? Increased again. How did that change or that increase compare to the previous increase? She wants slightly smaller. Agree? Let's look at another one. Here's the next one. What's happening to the changes in, we know that the vertical distance is increasing. What about those changes in vertical distance? Are they increasing or decreasing? They're decreasing. The changes are decreasing. So the amount of vertical distance is continually increasing, but by smaller amounts. The changes are decreasing. Is that concave up or concave down? Concave up or concave down? So the graph will be increasing, but concave down because the rate of change will be decreasing. Or something like this. So in that first quadrant, the changes, the vertical height is increasing. It increases from 0 to 1, right? Here that vertical height is 0, and at the end it's 1. And as it increases, though, the changes do what? Decrease. And so you get the concave down, the decreasing rate of change. Okay. Second quadrant. Does the height increase or decrease? The height decreases, okay? So those changes are negative. Are those changes getting more negative or less negative? The changes get, I'll do it again, ready? Watch. Do the changes get more negative or less negative? They get more negative. All right, so the height decreases from 1 to 0, but those changes get more negative. Are the changes increasing or decreasing? There's the key question. They're getting more negative. Decreasing changes. So the graph is still concave down. So watch it, ready? Last thing. First quadrant, the height is increasing, but the changes are decreasing. Second quadrant, the height decreases, and what about the changes? They still decrease because they get more negative, so the graph is concave down. So that's tracking this quantity of vertical height above the horizontal diameter for half a rotation. Half a rotation. If we only had 2 more minutes. Okay, so web work and written work, check Blackboard later today and tomorrow. Have a good and safe weekend.